Okay. Okay, Shreya.
A very good evening, everyone. The 19th webinar under IEEE brought to you by Malabar Subsection in associated IEEE Malabar Hub with KMCT CEW. Before we begin, I would like to request all the participants to mute your mic for other speaker section. Robotics and other combination will make the world pretty fantastic compared with today. And it will more into the robotics, we have with us a very special guest, Dr. Sreekanth Madhavan, CEO of Kabani Tech. He has a makerspace and product development center at Shornur, Palakkad. He has 20 years of learning in DIY engineering, robotics, and electronics, and 3 years of teaching experience. He is the treasurer of IEEE RAS, Kerala chapter during the years 2015 to 16, and active member of Robotic Society of India. He delivered talks at more than 30 engineering colleges on robotics and IoT. He also published 5 international conferences and 1 SCI indexed international journal. He is the man of distinct vision who has been in front in transforming and inspiring future with his work and spirited contribution. It is my absolute honor and privilege to invite Dr. Sreekanth Madhavan to today's section. It's over to you, sir.
Thank you, Shreya. I hope you are I'm audible, right?
Yes, sir.
Yeah. Okay. So I hope we can start. Okay. Okay. 1 minute. Can you see my screen now?
Yes, sir.
Okay. So today's session is basically on a different. Actually, I need to have different dimensions on how to design robots. So that's why I put the name in a different manner. So when you name that thing in English, it will be the nuts and bolts of robots. So it's better. I thought it's better to convey those things in Malayalam. So the class won't be directly in Malayalam, but the topic needs to be in a different perspective. That's why I put it robotokku venda nuttukalum bolttukalum engane theranjedukam ennakiyadu. So I hope almost all of you are from Kerala. So but still, as it is an IEEE event, so I will be making the presentation in almost English. So okay. So if you have any doubt, you can ask. Okay. So my degree is basically or BTech is in electronics, MTech is in signal processing, and a PhD is actually in an area of somewhat related to material science. That is, I worked on a material called shape memory alloys. That is basically a memory alloy. That is an alloy of nickel and titanium, which can act as a muscle equivalent of an human muscle. So I worked on the sensorless control of that kind of shape memory alloy at NIT Calicut under the guidance of Abraham P. Matthew and Dr. R. Vijayana. So I just mentioned all these things, that these things are possible even if you are sitting inside in Kerala itself. So from understanding the fundamentals of electronics to understanding the material science itself, we have a vast area of expertise even in our state. So that's why I'm really happy to be here. So, okay. So there is a disclaimer for my presentation here. Okay. So the disclaimer is that it's not normal normally. So the presenter doesn't give or any confirmation that the listener will be able to make robots, soft robots or bio-inspired robots after the class. No, the presentation is based on my perspective and my past experiences. So it won't follow any standard presentation approach. And of course, the conflict of interest with listeners are accepted and encouraged. That means you have every right to stop me in the middle and say that I'm talking bullshit and just stop the presentation, or otherwise we can argue up to any point on the things which I am basically have a problem, or you have basically have any trouble understanding those things. Okay, so we can start. So the discussion will be mainly focused on why this topic and why robotics. And as you are basically final year or pre-final years of your bachelor's, so I need to extend a perspective on the career as a robotic designer or a developer. How can we stand? Okay, so that I don't know how to elaborate on that, but still I will have my perspective on that. Okay, so to start with, I'm basically not a teacher, so I'm really sorry I can't teach you. Okay, so this is not a topic to teach. Actually, it's a topic to learn. So there may be several teachers, and you yourself will be a real teacher, because you need to have a lot of trial and errors while you are designing all these kind of robots. So it requires a tremendous amount of passion, purpose, perspective, and of course, a parrot attitude. And the main problem is, whenever we see or say that we love robotics and we are working on robotics, this is what it is happening. It's like several blind persons describing an elephant. So everyone is saying their own perspectives, but no one knows what it is. So this is the scenario of basically what the condition of robots as of now. The reason is that the class definition of robotics basically lies in the large spectrum of engineering, science, technology, and sometimes philosophy, and sometimes in arts. So it is difficult for us to engage in all these kind of areas and to get an expertise in all these things. So that's why I'm really afraid that these things are under not with the limit of any single person to handle these kind of things. But still, we can have an love or a passion towards all these things, and we can try. And that try goes till we die. So where are we now? So I will be explaining some of the stabilized or some of the modern robots in the market now. There may be several advanced robots, but still I've taken all these things because these things were basically given a paradigm shift to the conceptual or the normal thinking of persons in an engineering field. So this is a surgical robot. From a company called Da Vinci, and we are happy to see that even in Kerala, there are around 6 or 5 hospitals in Kerala now equipped with these systems. When I started my presentations during 2006 up to 2015, there was not a single Da Vinci robot in India. But after the 2011, I believe I have hearing these kind of robots in Chennai, Apollo Hospital, I believe. So people started going there, and I personally have communicated to one of the doctors who made the surgeries with the Da Vinci. And while visiting IIT Madras labs, I have been able to touch all these kind of actuators by my hand itself. So I can feel what kind of changes they have made to the conventional robotic surgery process it is. So when you are looking at, yes, it's a robot, what it is made of. If you have to tell that, I need to start from everything. So what you are basically seeing in these robots is that there are so many mechanical systems, electrical systems, and other than that, what are those things? There will be sensors, there will be so many actuators, and a patient is there, and a surgeon is there, and a person helping at the patient's nearby is there. So how can we again make an engineering perspective or engineering calculations, or how can we think that we can make a robot something like this? So how to start? So there is a point or a comma at our thought process, that where do we start? So that's the point we all are at when we are at our bachelor's, final years, or masters, or at PhDs. So the problem is these questions cannot be understood from a single perspective of a engineering background. No electronics, no electrical, no mechanical, no physical, no civil, no other part can single-handedly do all these things. So what basically this does, a surgeon is basically changing the moment or positions of those 6 robotic arms, which is near to the patient. So he basically changes his hand. The surgeon basically changes his hand at the remote console, and it basically translates those motions directly to the robotic arm movements, right? So that is the only thing happening there. But are these robots or the doctors are sitting very far away from the patient? No, he is basically sitting around 10 meters or 15 meters maximum at a distance of from the patient. So why do we need this? Why do we invest on crores of rupees to purchase these things? So that's a question. So can anyone answer that question? Why do we need a surgical process which is this much expensive and the doctor is just nearby? Can anyone answer? It's an open question, and the language is not a barrier. If anyone needs to answer, I'll be happy. No issues. Okay. So the main reason is that these kind of surgeries require. So I'm switching off my video. Oh, okay. I'll leave it. So these surgeries basically require a nearby process is that our technology is not that much if up to date, or maybe it requires a latency in transmitting all this kind of data. So we cannot risk the patient's life because of the latency of transmitting this kind of data. So it's still nearby. So a surgeon in USA cannot operate a patient in Kochi. So that's the problem. So is it the only problem thing? No. The reason why we require a robotic surgery is that there are surgical procedures which basically going for 6 hours, 7 hours, or 8 hours, something like that. So it's a natural phenomenon. It's a problem with every human is that we may become tired or we get fatigued, that even our hands will be having a vibration, right? So when a surgeon is operating for a long duration, these difficulties in our human behavior may cause error at the patient's end. So what these kind of machines does is that uh, it can basically detect these kind of tremors or vibrations at our human hand, which can eliminate it at the point of tremor, and those kind of vibration won't be transferred to the robotic arm or the where the end effector lies, right? So this is one of the example for that. So there are several objectives for that kind of a concept, but this is one of it. ഒരു സർജന്റെ കയ്യിലുള്ള ട്രമർ അല്ലെങ്കിൽ വേറെ ഈ അപ്പുറത്തുള്ള പേഷ്യന്റിന്റെ മുകളിലേക്ക് എത്തരുത്. അത് തന്നെ ഏറ്റവും വലിയൊരു കാരണമായിരിക്കും. And he can get multiple feedbacks also. So there may be the patient may be having a slight temperature increase or something like that. So the same thing can also be fed back to the surgeon itself. So it is basically a byway. Both ends will have sensors as well as actuators on that end. So that's the thing we need to understand. So it's a different perspectives, and we can still talk about those things in detail, right? And the other thing, this is an autonomous car made by a company called Waymo. There are so many companies right now who are making almost successful cars like Tesla. They have their own autonomous cars on the roads now. While I am presenting this in 2016, not a single car was there. But still, that the same slide is backward than in 2016. I'm really happy that I can see a different part of a world after I'm sitting in around 4 or 5 years now, right? So where do we stand here? So the entire vehicle is autonomous. We have basically gathered all the information from some kind of sensors called lidars, and there are vision sensors and all. Same, the engine, there may be engine, and almost Teslas are on electric vehicles. So those vehicles are controlled by motor drives and all, but the parameters which requires the turn, the brake and all has been automated by a computer, which is having an inbuilt machine learning algorithm, which is made with the data acquired over the period, and the same time with new data or new information available, the same model is keep on updating and all. Right. So we need to understand that the cars are basically trained for the US roads, but I know it's a road. We know basically it's a road, it's a car. Why? Can we put it that same car in Indian streets? No. We know that the terrains this and the conditions of the roads and as well as the things which I've learned at US cannot be here in India. Maybe it's at some part of India, but not all way long. So the understanding what it is, it requires training, right? So the changes are not for the vehicle, but the changes required to transmit or transport that vehicle from US to India is entirely or only on the machine learning algorithm, right? So here, what is the change required? It's only on the mathematical sides of these kind of development of cars, right? So here, what we see that here also machine learning is there, but there are so many important things to know here, because the minute movements of end effectors and the other actuations which require doctors to change the positions of the arm. And here, it's not minute, but the changes is still required because the velocity or acceleration is much larger compared to the patient doctor's hand movement. So the scenarios are different, difficulties are different, but there are some common background things which we need to understand while designing these kind of systems. So after these kind of 4 or 5 slides, I have basically put a numbered itinerary. What kind of things we need to understand or have to check before going to design a robot. May not be apt, but it will give you an understanding of what to do. Right? Okay. Again, so the initial one was a surgical robot, second one is a car, and third attempt is to get a companion for us. We are replicating, we are trying to replicate ourselves. So this is Sophia. So there are several newer versions or better versions of humanoid or human-like robots in the recent times, but Sophia is basically considered to be have a better PR. That is, they have a better PR team. That's the only thing, right? But what basically does is that we require a companion. We need someone to talk. We need someone to listen. So these kind of terrible conditions of human nature, human conditions can be resolved with a robot, something like this, right? So where do we stand now? So other than the same thing, machine learning or mechanical movements or material science, which is required to develop the skin, eye movements, and other things. Other than that, we need to learn the very fundamental approaches of languages. That is called natural language processing. Also, it is required. So here it comes to a new thing called material science design, and other than that, it requires a different kind of approach to natural language processing also, because like our conditions in roads, we have a conditions of our languages also. So we know that the slang at Trivandrum is not the slang at Thrissur. It's entirely different. Even the person from Trivandrum cannot understand what he's saying at Thrissur. So there are problems, right? Okay. 1 minute. Yeah, okay. So so that's why I put in another slides also. We know that robotics requires mechanical sides, electrical, electronics, and software. But a different kind of algebra or a mathematical approach is also required for understanding or developing new kind of robots. So when we try to say it's a robot, it doesn't mean that it requires a physical structure itself. It can have a pure software approach also. That thing is, by definition, I believe that a robot is something which automates some process completely. So if a device is basically communicating well, that is something like Alexa. Yeah, I can say that it's basically a robot. So what is the new thing? It's basically the algebra behind it, the mathematical process behind it, right? So how do we know these things? So to understand algebra, we need to go back to the basic requirement of number systems. So how do we start counting everything? So while we have an understanding of when we have an understanding of this kind of real line, then we need to understand the basic numbering systems of computers. So maybe the quantum computing will basically revisit the entire understanding of thinking of the computational process and all. But still, at this time, we have a certain standard processes. So we need to have a better understanding of algebra and those which leads to vectors and all. So for machine learning and better understanding of all those things, we require better understanding of, I will prefer to say that we will need to have a better understanding of the real line, right? So what is basically associated with this? So it may require understanding the history as well of computing itself. Okay, so then only we can have a paradigm shift in thinking, because everything starts with the fundamentals of our textbooks, which starts at the mathematics or from the understanding of basic physics and all. So I will basically say that we need to always learn, relearn, unlearn, and relearn our fundamental principles. That is, we should never left alone our textbooks from, I believe, from 8th standard to 12th standards. We need to have a relook always. So we need to have it. We need to check on the void where we left some things, because only then we can have a entirely new product. Okay. Okay. So this is a small robot. You can see that it's a size of only 20 millimeter. So what it does is basically jumps. So what is new in it? It's basically a flea. So I was working on the same material for around 6 years. So it's called a shape memory alloys. So this device or this structure is a kind of inspired from origami. So you can know that these origami structures are basically made a long way back. So they are having a large, even in the James Webb Telescope, which NASA sent to outer space, is again the antennas and reflectors were all folded with the help of these kind of origami structures. So similarly, we can have a revisit to every element for getting new design approaches. So this is basically something like that. The thing which is like a spring-like thing is basically a material called shape memory alloy. You can see what it is doing. It is made with some kind of new material called it's a composite material. So the PCB is itself on it. You can say it is a kind of flexible PCB, but it's not flexible that much, right? So tension is going on. Now it will jump. See, now the slow motion will come with a 3000 frame per second. See, it jumped. So there is no conventional actuators like motors, pneumatics, hydraulics, Nothing. The entire actuator is a material composition called nickel titanium copper or nickel titanium, which is commercially named as shape memory alloys. See how much for a higher it's basically jumping. The weight of this device is only 2 gram or 3 gram. So if you blew, it will go a large distance, right? Only that much weight, 2 gram or 3 gram. So with conventional actuators, we can't design such kind of a device. Can we get an actuator at 2 gram or 3 gram? No, never. So that's why people are working in material science field to get new information and all. So, and that's why I will turn my screen, and you can see that there is a periodic table in my office itself, which basically every time we itself need to I put it in that way because we need to have a revisit on every material possible at every day, because we don't know what kind of surprise is there waiting us. Okay, so we don't have that kind of facility to do that, but there is no limit of thinking of dreaming. So that's why we have have a look at the periodic table on every day. Right? So again, it's a jumping robot. So there is nothing new. So what is basically new in it? No, nothing is there new, but they have revisited or redesigned the gyroscope. So they some kind of stored that momentum and just uh, made it to push further from the ground. So that's a new design, something like that. So similar designs are there for a long time, but I thought you should have a look on that. So that's why I put it. So the conventional actuators, sensors or motors or pulleys have been used, nothing new, but they arrange different manner, right? So that's important. So you need, how can we think of something like this? We need to have always have a better idea of how toys basically works. So then only we can develop new things, right? So what are the design steps of robots? So how do we design a robot? So that's a question we need to ask. But I know not every part. I know only a small part. That's why I put it almost in the bracket. Yes, mechanical design is there, electrical design, power, mathematical modeling, algorithm, software, control system design, motion planning, bar path planning, and robot calibration. All these things are basically required as a backbone for designing any kind of robot. So the mechanical design basically includes not only the structure, this mechanical design also includes the material perspective of selection of those kind of structures. So what kind of materials, what kind of composites we design, what kind of composites we take, even what kind of nuts and bolts basically we take while designing this kind of robots. Because the problem with mechanical design is that, take a look, if I am making a robotic arm, something like this, right? Robotic arm. So there is a one joint and second joint there, or a three degree of freedom robotic arm. The problem is, how do we, when we design each and every joint or these links, how do we combine these links to other links? See, it requires fasteners, right? Nuts and bolts, something like that. So what happens when it is moving from one point to another? Is it smooth like this? Somewhat what we are moving? No, it requires an initial acceleration, a steady state movement, and a final deceleration. So when these acceleration, steady state moment and deceleration occurs, it basically generates a lot of vibrations back to each and every joint. So each and every joint basically vibrates. What happens then? This kind of that basically having a stress on the point where it is basically fixed. That exert basically a design on the nuts and bolts. So in the down, nothing will happen, but it will just fall apart or break apart. So fastening things is also a, a, a design challenge on any of the robots, because every vibration has to be damped when it is generated, or there should be counterbalancing mechanism to every designs. So we can every person basically having a love of Royal Enfield bullets. So you can think the bullets has been there from 1960s or 1930s. I don't know the exact time. But the problem with bullets, even at the 2011, or I have a 500cc bullet, is the problem is that it's vibrates. It's vibrate to every part. When a rider with only his passion, basically when he is riding, he is okay with it. But on the long run, every joint in that man is going to have a problem. So what to do? I believe that at the newer models of bullets or the Royal Enfield machines, they have made or at least understood the requirement of damping vibration from the beginning, that is from the engine. So it became design of silent engines from them. So that's the thing. So, you can see those things from the Japanese cars and all, like Honda and all. They are suicidal because every part is counterbalanced. So we learn those things with a gap of around 60 or 40 years. So that's why I put the name of our class as the nuts and bolts of robots. It's not about nut and bolts, but it's about the requirement of detailing very minute portions of or areas of engineering, right? So we may think that okay, we have made something, but the problem is in the longer run, we don't know what kind of problems are coming to arise at different perspectives, which we may not have aware of, right? Again, the electrical design. I'm not detailing in every part because it's already 6 o'clock now. I believe it's up to 6:25. So this is about electrical design. Even in electrical design, yes, it's not only about the current flow. It's about the generation of heat. Right, every current flow it makes heat also. So how do we minimize those kind of heats? It requires again with a part of combination of mechanical itself, but still the selection of wires, selection of clamps, selection of PCB trays widths, everything is a part. I'm not saying entirely on the electronic side, but still, and you know that there are electronics behind it, but still, I'm saying only on the failure pointer and the power sources. How do we select the power? So we have we are basically working on a 4-wheel robot now for around 4 or 5 months. So the client requests basically that robot to power a 600-watt load at the starting, but in the middle, client basically upgraded to 600-watt to 1.2 kilowatt. The problem is up to 600-watt, we know what are the power sources which is required, but when it is jumped to 1.2 kilowatt, which is basically near to a power of powering a home, the problem is selection of inverters, and not only that, it basically have hindrance of selection of battery. So which kind of batteries we take? There are plenty of batteries on there. So in the normal lead acid is there. If we are taking lead acid batteries, we require around 100 Ah and 24 volt. So the lead acid batteries may weigh around 60 to 70 kg. So can you assume that a vehicle with 70 kg, what kind of structural design and torque requirement to each and every wheels it is required? It's too much. So what we does is we check for a newer battery designs or battery design methods, but it requires tremendous amount of money over that. But there is no other view. There is no other way. We went on selecting a new kind of battery for us. It was around 4 times the normal money than the conventional batteries, but there is no other way. Right. And I'm just skipping the mathematical modeling now. And so I'm telling that these kind of things happens normally, right? And the algorithm, yes, the algorithm is basically always or keep on updating, and updating. And there is nothing called a final algorithm. It requires always updation. So you need to open your ports to design of every board so that you need to understand the system what you have developed requires an updation in algorithm, right? Like what we have told in the first of updation of Tesla's machine learning model, right? And the software. Software is basically framework, basically required word to communicate from one to other, right? So software in robots, basically you can say that it requires a robot operating system. In the similar name, there is an operating system called ROS. So what is the requirement of ROS? So there are requirements. The reason is that when you are making a robot with Arduino or something like that, it is basically running in the uh, 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 code and sequential manner. But the problem is none of our processes are basically sequential. They are basically independent things working in independent threads. എല്ലാതും separate ആണ്. At a time real time operate ചെയ്യുന്നതാണ്. So how do we make it? We require multiple threads to run at the same time, and those threads should handle different independent problems at the same time, and those problems should be communicated to each other. So I will explain in a simpler way. So I have a robotic arm. So the robotic arm has to move from one point to another. The problem is how to move. So it requires, that is, I need to move from x1, y1, z1 point to x2, y2, z2. So how this movement is happening? So it requires fundamental understanding of kinematics. So if I know the x1, y1, z1, x2, y2, z2, I need to understand the theta 1, theta 2, and theta 3 of, that is, angular moments of each and every joints in the first place. So these angular moments to be known. So what we do the inverse kinematics. Am I right? So with the known value of inverse kinematics, we basically put all these finding theta 1, theta 2, theta 3 values in independent threads. There is no other way. We need to spread it in independent threads in real time. Otherwise, if we go for inverse kinematic calculation, one of our joints will move at first time, and it will take some time to calculate the other angle, and it will move then. And so the movement will not be smooth as you think, right? And other problem is there. Other than so that is basically coming in the mathematical modeling thing. So that's why I keep up to software, right? So other than the kinematics, when you are thinking of putting a weight on these links or in the load, or you are thinking a kind of a load, then we need to have a dynamics also, the dynamics calculation also. So when the dynamics calculations comes, basically we get all these kind of torque requirement, acceleration requirements and all, right? So and combining this acceleration requirement and torque requirement, we basically get the vibration analysis at each and every joint. So this is what is happening, and for every point that is then that is a requirement is that problem with this kind of dynamics and kinematics, we may not get the exact values what we are thinking of. So what to do then? So we need to have a control system to control each and every subsystems to the control of the entire larger systems. So it requires the understanding of the total mathematical modeling of the entire system. So that is the thing. So how do we mathematically model these things at start? So we can come on that, but there is a requirement for that, right? So is it required a mathematical modeling every time? No. The reason is that when you are doing these things in an engineering way, or you have to make some concept into practical. So you can think of selecting an exorbitant large amount of, or twice or thrice the amount of data. Either if I'm selecting a motor, I need to move, make a four-wheel robot which can move around 10 kgs from one point to another. It has having a 4 wheels. So at present, we can select a larger amount of torque of motor and fit it with a motor drive, program it in Arduino, and you can have a remote control. Yes, it will move. But the problem is, how do we optimize the price? Then we need to have a mathematical model and everything. We need to make the torque calculation for every motor. Then by the 1.2 or twice times of the torque, which is basically got by the mathematical modeling, then you can optimize the price. So, but in the start, when you are a kid, you are free to select on your choice for making robots. But if it is for the larger run of making thousands of lakhs of robots, the problem is you need to optimize. So then we need to have a mathematical modeling on that. Am I right? Right. Then comes with the motion planning and path planning. Let's see. You have made a robot which is basically like a Mohanlal, and someone, sorry, a humanoid robot. But if it is want to walk like Mohanlal, it walk like Mammootty, it's two different things. So that's why we need to have a perfect motion planning for everything. And to which path it should go is an entire different process called path planning. And other than that, if you are making any kind of robot, it requires precise robot calibration. It has to be done independently, right? So when you are doing the robot calibration, there is a point is that at some point you will understand that the entire redesigning of structure may be required. Yes, that's what Boston Dynamics and all have been done for the past several years. They are the company where none of the robots are basically not for sale before 2 years. They sold a robot only just 2 years back to some academic institutions. So until then, what were they doing? They were working on the algorithm design of everything. But still, who are their funders? Every giant basically funded them. Who wants them now? Is Hyundai, right? SoftBank, Google, everyone bought them, and they don't know what to do with them. The problem is it is still futuristic. The money will flow only after 20 or 30 years, right? But still, those kind of systems are basically required at a in the future. Okay. Yeah, 612. Okay. So mathematical modeling. So I'm telling this kind of mathematical modeling always to you. So what is this? Yes, you are basically doing these kind of things in independent engineering streams for at least 2 or 3 years, or maybe from your starting of 8th standard itself. So if you are taking at an electronic circuit, you need to have a mathematical model that. Then we basically do is that we have a RLC circuit, and we have, and we need to have a transfer function for that. So what is the transfer function basically gets what the system is possible of, at what basic fundamental frequencies basically it will work unstable, right? So this is what it is get. Okay, so for that you basically draw the schematic diagram of the system and define variables. And second, what you do is using physical laws, write equations for each component, combine them with according to system diagram, and obtain a mathematical model. Right. So like KCL or KVL, which was voltage law, this was current law. Then to verify the validity of the model and its predicted performance, obtained by solving those equations of the model, is compared with experimental results. The problem is with mathematical model is that once you get a mathematical model, you should not think that it's a final thing. There may be issues with the selection of variables and values which you have thought. So in order to verify the mathematical model, you need to make a model in physical things itself. You need to make a physical model, right? So this is the question of any validity of any mathematical model can and be answered only by experiment. പരീക്ഷണങ്ങളിൽ അല്ലെങ്കിൽ എക്സ്പെരിമെന്റിൽ ഒരു സാധനം ഉണ്ടാക്കാതെ നമുക്ക് മാത്തമാറ്റിക്കൽ മോഡലിനെ കുറിച്ചിട്ട് ഫൈനൽ വേർഡിൽ പറയാൻ പറ്റില്ല. So that's why even the ISRO അല്ലെങ്കിൽ നാസ ഇവരൊക്കെ വിടുന്ന സാറ്റലൈറ്റ്സിനൊക്കെ അവരുടേതായിട്ടുള്ള ഒരു മാത്തമാറ്റിക്കൽ മോഡലും അതിന്റെ പരീക്ഷണങ്ങളും ഉണ്ടാവും. So we are seeing some kind of failures is that this kind of mathematical models may be failed during the initial approach. So this is not my words. This is the words by Ogata, right? There is a book called System Dynamics by Ogata. You may have learned the control system by Ogata, but the problem with that book is it's basically have a preceding book. It's called System Dynamics. Okay, so go to your library and start checking for System Dynamics. You can enjoy reading better perspective of control system by starting with System Dynamics. Okay, and applications of robots. So I'm going to the final slides of that. Application robots and machine learning, the same or the simple ones or the still required ones. Okay, so pick and place operations, welding, painting, inspection, medical, military, home automation, of course, leisure, and many more. Okay, so this is one of a you can say it's a robot. This is me a few years back. I'm on a Segway. It's basically runs on 2 wheels. There is basically an inbuilt control to stabilize these things. But I am basically the person who is basically unstabilizing or troubling that control mechanism. But with a few trial and error, it's basically easy to maneuver all these things easily, right? So there are so many robotic arm or manipulators, which is some of them are 4-wheel robots, and this is one of the industrial robots, Sekuka KR210 to SC2. So what you need to understand is that when you are designing a robot, you need to understand who are basically your competitors or who are the main vendors in the market. Please go through their specifications, then only come back to design your robot. Okay. So what are the characteristics? Yes, a payload, reach, precision, repeatability, DF. Okay, actually these all things are basically coming under the nuts and bolts. Okay, so it all requires when you are designing a robot. So still there are around thousands of different stringent approaches which we need to take care of, but in 1 hour it's impossible to talk all that thing, and I don't know everything. Okay, and you need to have a better understanding of end effectors. So you sometimes you need to hold an egg, but sometimes you need to hold a huge steel bar. Sometimes you need to hold a very fragile object. So with that, these kind of end effectors, which basically is at the end of any robotic arm, has to change. How to select all these things, it's an again different area of expertise to be thought of. Okay, you can have a PhD only on that. So new research directions other than these are the material perspective, material design of in every manner, actuators, material structures, everything. Okay, so you don't worry about whether you are electronics or computer science, but still you can have your own hands with these kind of new researches, because in the newer coming era, interdisciplinary research and developments are basically allowed at any of the universities, because they have understood what it is required to have a faster growth in our future. So every university is accepting interdisciplinary masters and PhD program. So please look at those things. Okay. So I'm just giving a case study. So this is a small granular gripper basically designed by one of my students earlier 2 or 3 years back. So ഒരു granular gripper ആണ്. So You can see there is an bubble which a small kind of grain is basically filled in that. When it is inflated, it is basically make a bubble on that. And when it is deflated or decompressed, so it basically holds anything which is in the middle. Just made a plunger kind of a thing. It basically holds at this position. Okay. Okay. I believe I can show it at another time. And how do we make all those things? We basically modeled those things at the first end. Then we made a 3D model with that. And by using 3D printer, we made these devices. Okay. So similarly, there is a soft gripper. See, there is a soft gripper. It can hold. So how do we make those fingers? It is basically an silicon mold which we made first. This is basically an finger design, and we made a mold for that. And we pour the silicon from these points, and see, and this is silicon, and we made these silicon fingers. So these are things are possible even at the BTEX level. There is no issue. See, another kind of 4-finger mechanism is there. See, this is also made by us. These are basically kind of hobby products. So not our products can be shown as in this video because I have some NDA with the clients. So see, we can make different kind of grippers, something like that, even at our premises itself, no issues. These are basically 3D printed. Right. So I'm basically winding up my session. That is, when we are thinking kind of every things in detail, you need to understand it. There are so many different things to be learned, even from a single thing like nut and bolts. Okay, so there are so many kind of nuts, there are so many kind of screws, and there are so many kinds of bolts. You need to understand where to fix or where to put all those things and understand your applications better. Okay, so thank you. If you have any questions, you can ask me. Okay. I think someone is. Okay. It's not easy to start this kind of robotic project at the beginning, but yeah, I think someone is trying to have a chat.
Audience, if you have any queries, you can put it in chat box or directly unmute and you can ask. Sreekanth sir, if
Anyone
you
asking
like,
questions?
yeah,
Actually,
if a student is a real beginner, where from he or she can start in learning robotics? Sir, Sreekanth sir.
Yeah, if there is no questions, then I think we can
I have a general
wind up
question.
this session.
One
Am I
general
right,
question.
Sadiq sir?
I have a general one question.
Hello, sir.
Yeah. Hello. Hello.
Yes, sir. Yeah.
Yeah, I
Anyone?
have a general one question. Like, if a student is a real beginner, doesn't know anything, and where from he has to start, he or she can start learning about robotics.
No, everything. It's like learning Kung Fu, sir. Everything you do is Kung Fu. I think it's from that movie. So whatever you do in practical but with your passion is
Yeah.
robots. Nothing
Yes.
more, sir.
Okay, fine. Okay, Shreya.
Okay, sir. Thank you so much, sir, for the very encouraging section on behalf of IEEE subsection of KMCT CEW. I'd like to extend our deepest gratitude to you for providing us most invention about robotics. For taking the significant perspective of time, thank you, sir, for your wonderful section.
Thank you. Thank you all. Okay.
Thank you, sir.
We have come to the conclusion of our webinar. I hope you have been inspired by unparalleled of learning, thoughts provoking and the site of section is given. I would like to thank everyone that have been involved in the organization of this program for the dynamic effort. Once again, thank you all for your participation. Please note that feedback link has been posted in comment section. Do go through and fill it up. Thank you. You may leave now the meeting.